Hello guys, today I will explain for you the idea of P-delta effect and how we can check this effect and include it inside ETABS software. And to include this effect inside ETABS software, we can use one of those two options shown here, and that's all what we need to do actually inside ETABS, and the program will do the rest of the job for us, okay? Then it is important now to understand what is going on inside the software while we include the P-delta effect, instead of showing you how to include it inside the software, okay? And for that reason I have prepared this slide or this PowerPoint presentation that shows a lot of details about the P-delta effect, okay? And by reading the first sentence here, P-delta effect is one type of the geometric nonlinearity which involve applying the equilibrium equation at the deflected configuration. Then after this structure deflects due to lateral loads, we are particularly concerned about what is going on when we include the equilibrium equation with the existence of those gravity loads. And as shown here, the bending moment diagram have three parts or three triangles. The first one is actually obtained from the first order analysis, which means we apply the equilibrium equation based on the undeformed shape. And then in this case, the bending moment diagram of this cantilever column will be equal to h multiplied by the height. While there is now two sources of contribution to this bending moment if we include the P-delta effect. The first one is called P big delta, which is associated with the displacements of the member ends, while P small delta contribution is associated with the local deformation happening locally to the member itself. Then due to this curvature or due to this bending, this column is not now straight lined and there is local deformation happening here at the middle, for example. Then P small delta accounts for this local deformation. And the P big delta may contribute to the loss of lateral resistance and dynamic instability. Therefore, we can say that the P big delta is just the global response happening to the structure, while the P small delta is something related to the response happening locally to the member itself. And as shown in figure 3, which is taken from Peer ATC 2010, there is a reduction in stiffness when we check the force deformation relationship and we compare the first case, which is without P-delta effect, with the second case when including the P-delta effect. Of course, the P-delta effect have this slope which is negative actually, because the P here is negative as it is a compression force. Then the Kn here refers to the geometric stiffness, while K0 here refers to the elastic stiffness. Then when we include the P-delta effect, we need to subtract the geometric stiffness from the initial stiffness, and that's why we have this reduction in stiffness, okay guys? And going to the next slide, I'm using the same cantilever column to develop those equations as shown here. And now the general formula for the bending moment of this cantilever column can be expressed using this equation. And of course, this equation is now function of x. And x is just the distance covered from the top of this cantilever column to the base. Then by applying the equilibrium equation and summing the moment around the base to be equal to 0, we can generate this formula shown here. And please note that the small v here refers to the local displacement happening to this member. Then if we assume that the column will deflect to this dashed line here, we can neglect the last term, which is multiplied by the local deformation. Then in this case, the formula will be equal to those terms without the P multiplied by V. And if we take the X as a common, we can express this term, which is P multiplied by delta divided by H, as delta H. And as shown here, the P-delta effect on bending moment is similar to having an additional force delta H applied to the structure. However, we don't have additional force applied to the structure, but we have additional force generated inside the structure due to the gravity and to the horizontal force applied to the structure. Or in other words, due to including the P-delta effect. And now if we substitute H instead of X, we will have this formula here, which is the base moment of this cantilever column. The first term refers to the primary moment that could be obtained from the first order analysis or based on the undeformed shape of this structure, while the secondary moment is obtained by including the P-delta effect, okay? And now to satisfy equilibrium, we should have a shear force applied at the top here, and it should generate the same bending moment when P-delta effect is included. Then I donated this new shear force to be V bar, okay? And by setting equation 1 and 2 to be equal, we will have this equation here, Hence, the new shear force of this column or this cantilever column will equal to the primary shear from the first order analysis plus P multiplied by delta divided by H, and this is actually the additional force inside the system itself, okay? Then by going to this slide, we can see that the shear force from the first order analysis will result in this displacement donated by delta 1, while when we include the P delta effect, we will have additional shear force inside the system, and it will result in a higher displacement when we compare it to the first one. Hence, the P delta effect will induce additional shear forces and additional displacement. And by normalizing equation 3, we can have this formula here. And keep in mind that this is the ratio shown in ASCE 710, which is the stability coefficient. And this term is just the ratio of the secondary moment to the primary moment. And please keep in mind that the ASCE 710 uses the design story drift in this formula. Hence, it is multiplied already by CD over I. Then they multiply again the whole formula by I over CD. Hence, they are trying to say don't amplify the design story drift used in this stability coefficient formula, okay? And in this slide, I'm showing this example for a simply supported beam subjected to those distributed uniform load and to this axial compression force. And due to the applied loads, this beam will deflect to this configuration. Hence, now we have two sources of contribution to the flexural bending if we want to apply the equilibrium equation based on the deflected configuration. The first contribution comes from the elastic stiffness of this beam, and as all of you should know that the maximum moment of this simply supported beam should be at the midspan. Hence, the maximum moment here would be WL square over 8, plus the contribution which is coming from the relation between the applied axial force and the deflected configuration of this beam, and the additional moment will be equal to P multiplied by the small delta here at the middle. Hence, the total moment will be equal to those two terms here, okay? And in this next slide, I'm showing also another example for a cantilever column. However, the first one bent in a single curvature shape, while the second one bent in a double curvature shape, okay? And the difference between both examples is that the influence of P small delta is more or much higher in the first case, while it can be neglected in the second case. For example, in the first one here, there is a small local deformation at the middle. Hence, the geometric stiffness will contribute to the bending moment as shown here in this shape. And the total moment now is equal to the elastic contribution plus the geometric contribution. And please note that the maximum bending of this column is occurring here at the middle somewhere. While if we check here this figure now, the maximum bending is happening at the base. Hence, when the column bends in a double curvature shape, the inflection point is somewhere here at the middle. Hence, the displacement occurring here at the middle is now equal to 0. And what is more important here is to consider the P big delta, as it have more influence or effect on the flexural bending of this column. Hence, guys, this slide shows how the end conditions affects even the development of the internal forces inside the member itself, okay? And here I have included now many details taken from Dr. Paul's book, which is called Modeling for Structural Analysis, Behavior and Basics. I advise every one of you to read this book because it is very important, guys. And by reading this paragraph, if a structure has inelastic components, its behavior will be nonlinear, and this is usually referred to as the material nonlinearity. However, we can obtain nonlinear behavior even if the structure remains in the elastic range, but this could happen when a structure undergoes large displacements, and this is actually referred to as the geometric nonlinearity. And there are two causes of the geometric nonlinearity. The first is based on equilibrium and the second on compatibility. And starting with the first cause, which is equilibrium, and by checking this figure here, if the equilibrium equations are applied based on the undeformed position, the force in the spring is equal to H, while if we apply the equilibrium equation based on the deformed position, the force in the spring is now equal to H plus P delta divided by the height. Hence, doubling the H and P will not double the force in the spring, and hence we will get a nonlinear behavior which is caused by the equilibrium equation which are applied based on the deformed position. And going to the second cause, which is the compatibility, And the compatibility actually concerns the relationship between the displacements of the structure and the deformation of its components. Hence, if we check here this column after it deflects, we have a new length because we have deformation, and the new deformed length is just equal to the square root of h square plus delta square. Hence, the compatibility relationship is just the relation between the bar extension and the displacements. And of course, the bar extension is defined as the deformed length minus the undeformed length. Then for very small horizontal displacements, the bar extension is close to 0, while for large displacement, the bar extends with a nonlinear relationship between the displacement and the extension. Hence, from this understanding, we can generate the three types of analysis. The first is based on the small displacement analysis, which means applying the equilibrium equation based on the undeformed position, and for the compatibility, the displacements are assumed to be very small. Hence, in this first case, we can say that the first order analysis is just enough or sufficient to get an accurate result, while in the case of obtaining large displacements, we need to use the true large displacement analysis or P-delta analysis. Of course, both analysis deals with applying the equilibrium equation based on the deformed position. However, in true large displacement analysis, the displacements are assumed to be finite, while in the P-delta analysis, they are assumed to be very small, okay? Hence, if we check those figures here, we can see that the theta, which is actually the angle here, is used in the computation of the forces, while in the P-delta analysis, theta is ignored. However, in both cases, we will get a nonlinear behavior. And to understand more the importance of using the correct analysis type, I'm presenting an example that demonstrates the significance of selecting the correct analysis type. In this example, it is assumed that the bar is axially stiff, meaning it has a negligible axial deformation, and we have two cases to consider. In the first case, the axial force P is set to 0 and the drift ratio is set to 10%. Here, all types of the analysis yields the same results. The force in the spring is H and the axial force in the bar is 0. However, in the second case, with the P over H set to 5 and the drift ratio is still 10%, we got different results. For a small displacement analysis, the force in the spring and bar are H and P respectively, while in the P-delta analysis and the true large displacement analysis, the force in the spring is approximately 1.5 H and 1 for the axial force in the bar. Hence, from those results, the P-delta analysis and the true large displacement analysis produce very similar outcomes, while in the small displacement analysis, the force in the spring is only H, which is less than the 1.5. This means that the small displacement analysis can lead to error, especially when there are significant gravity loss and large drifts. Also, we can understand that it is important to consider P-delta effect, while it is not always necessary to use the true large displacement analysis, which requires more computational effort. Then P-delta analysis is sufficient for most cases, while the true large displacement analysis becomes necessary for very flexible structures such as cable bridges. Okay, guys? And by checking this slide here, all of those informations have been explained before in the previous slides. Then I just want from you to keep in mind that this figure corresponds to figure 6.1. And in this slide, I'm trying to show now the relative importance of P big delta and P small delta contributions. For the cantilever column in figure 6.1, the P small delta contribution accounts for roughly 18% of the total P delta effect, with the P big delta contribution accounting for the remaining 82%. And by considering a more realistic case for a column in an unbraced frame, which is shown here in this figure, we have two cases, when we have ridged beams or when we have deformable beams, and we have a case that takes into account the rotation at the base. And by assuming that the beams contribute 1/2 of the total drift, the bending moment is now reduced by a factor of 2, and as a result, the P big delta and P small delta contributions are about 90% and 10% respectively. Also, if the beams are more flexible and contribute 67% of the total drift, the P big delta and P small delta contributions are about 93% and 7% respectively. Hence, if we take into account the flexibility of the beams and at the same time the rotation that could happen at the base, we will have less bending now in this column due to the rotation, and hence the P small delta contribution is reduced. Because the P small delta contribution to the bending moment diagram depends on the deflected shape of the column. Hence, we got now less deflection, and that's why we will get less contribution from the P small delta. Okay, guys? And now if we want to talk about the modeling of P big delta and P small delta, we can check this slide here. And please note that this slide shows the model only and not the analysis method. And regarding the P delta and the P small delta contributions, they should be modeled separately, or they can be modeled separately. And the P big delta contribution is straightforward and easy to model, while the P small delta contribution is more difficult. And by checking this model for a cantilever column, it is divided into three parts now. The small displacement column, which is located at the middle. This has the same end conditions as the actual column, which is fixed at the base and free at the top. And we have another part which is called the P delta strut, and this element is used to model the P big delta contribution, while the P small delta cable is used to model the P small delta contribution. Then after this column deflects to this shape, and as shown here, the P delta strut remains straight without any local bending. Then in the P delta strut, we are just concerned about the force transmit in this link here, which is the P delta divided by H, while the P small delta cable is now capturing this local deformation. And using this link here, the force will be transmitted, but it depends on the deflected shape of the P delta cable, okay? Hence, this just gives you an idea on the modeling technique that can be used to model both contributions. And regarding the reduction in the stiffness when including the P delta effect, we need to understand that when we include the P delta effect, the geometric stiffness is subtracted from the initial or the elastic stiffness. Then due to this reason, we will have reduction in the stiffness even if we are assuming an elastic material. Hence, guys, we could have elastic material, but we have nonlinear behavior. And of course, this is something different than the material nonlinearity, which accounts for the cracking and yielding. But what we actually do in practice, we provide estimate reasonable values for the stiffnesses of the members, accounting for cracking and yielding. For example, in concrete structures, we reduce these stiffnesses to account for cracking, which is something we have already done in ETABS. However, when we include the P delta effect, there is an additional reduction in stiffness due to the geometric stiffness. Also, by reading here for elastic analysis of steel structures, it's been common practice to base the element bending and axial stiffnesses on the initial elastic modulus for steel. And unlike concrete structures, we don't typically reduce the stiffnesses of the steel members. However, nowadays it is common to specify an effective modulus smaller than the initial elastic modulus when designing steel structures, which is a key difference between the two materials, okay? Also, it is important to understand that the P delta analysis is known as the second order analysis, and including the P delta effect in our ETABS model means we are performing elastic nonlinear analysis. And if we don't include the P delta effect, we can say that we are performing elastic linear analysis. And lastly, I'm showing here how we can develop the geometric stiffness based on this example, okay, guys? And please note that this example shows the physical procedure that can be used to develop the elastic and the geometric stiffness, which is actually not a general procedure that can always be used, okay, guys? Then in this way, we are just trying to understand how we can develop the elastic and the geometric stiffness instead of going into the mathematical details. And as shown here, the P delta column consists of a stiff elastic bar plus a P delta strut. Hence, we can divide this example into two parts, the first one dealing with the elasticity of the member, while the second one dealing with the axial force applied here, assuming that the strut has no elastic stiffness. Hence, here we are dealing with the geometry itself, while here we are dealing with the elasticity. And for this member, 4 degrees of freedom are used, 2 per each joint. Hence, to generate now the elastic stiffness matrix, we need to apply a unit displacement in the direction of each of the degree of freedoms, and we need to check the end forces which are donated by the capital Q. Hence, if we apply a unit displacement del Q1 here, this will result in 0 forces generated inside this member. While now if we apply del Q2, this will impose a compression force inside the member, since this member was assumed from the beginning to have an axial stiffness. Hence, the force generated inside this member will be equal to the axial stiffness multiplied by the displacement applied here. And to satisfy equilibrium, we should have another force applied in the opposite direction, and that's why the negative sign is used here. And we need just to impose now del Q3 and del Q4 as we have did here. And please note that each case will define one of the columns inside the elastic stiffness matrix as shown here. And now, by assuming that the strut has no elastic stiffness, and we need to apply here the axial forces at the top and bottom, and we need just to do the same. We need to apply unit displacement in the direction of each of the degree of freedoms used. Hence, by applying del Q1, this will result in developing end forces equal to those terms. And of course, we can get those values just by applying the equilibrium equation based on the deformed position. We can, for example, sum the moment at this joint, and this will give us the value shown here. And if we impose now del Q2, this will result in zero forces because this member is assumed that it has no elastic stiffness. Hence, each case of those will define one column of this geometric stiffness matrix. And at the end, we need now to subtract the geometric stiffness from the elastic stiffness, and in this way we will have a reduction in stiffness. And that's actually what ETABS do when we include the P delta effect. And after this long discussion, let's check how ETABS deals with the P big delta and P small delta effects. For the P big delta effect, ETABS considers this effect directly instead of using the empirical sway magnification factor in the code, which is denoted by del sway. While the P small delta effect in ETABS is considered using the magnification factor in the design code, and it is denoted by del NS or delta non-sway. Then guys, for the P big delta effect, we need to follow this procedure shown here, while for the P small delta effect, we need to use the magnification factor, which is delta non-sway. And we have an easier way to capture this behavior by dividing the element into multiple segments, and in this way we can capture the behavior and transferring it to the P big delta effect. However, it is not advisable to model P small delta because it may significantly increase the computational time without providing useful information. And from this explanation, I want you to note that the consideration of P delta effects is directly related to both the analysis and design of the columns. This is because the empirical sway or non-sway magnification factors are directly related to the design of the vertical elements. Hence, it is very interesting now to check the ACI code requirements regarding the design of the columns. For example, for short columns in a sway or non-sway frames, or unbraced or braced frames, we can neglect the P big and the small delta. And when the slenderness effects should be taken into account in a non-sway frames, we should neglect the P big delta effect while the P small delta effect shall be considered. And in this case, ETABS will calculate the delta non-sway accounting for the P small delta effect. While if we are dealing with a sway or unbraced frame and we need to take the slenderness effect into consideration, we need to include the P big delta and P small delta effects because both will have a big influence on the structural behavior and at the end on the load demand on each structural element. Hence guys, from this we should have now a clear understanding on how the P delta effect is related to the design of the columns. Lastly, let's check ASCE 710 regarding the P delta effects. And as shown here, the P delta effects on the story shears, moments, and the drifts can be neglected if the stability coefficient doesn't exceed 10%. And keep in mind that the P here corresponds to the total vertical design load, and no individual load factor needs to exceed 1. Hence, we don't need to use the factored loads, and we just need to use the service loads or the actual loads because we just want to check the actual response of the structure. And as I have told you before regarding the delta here, which is the design story drift, it is already multiplied by CD over I. And the whole formula here is multiplied again by I over CD. Hence, we don't need to amplify the design story drift, and keep in mind that the design story drift that should be used here is occurring simultaneously due to shear forces here. Then we need to use the same shear forces that induces those drifts. And as shown here, the stability coefficient shall not exceed theta maximum, which is limited to 25%. Hence, if the theta here obtained is larger than 25%, we can say that our structure is unstable, and we need to do some modifications to increase the lateral capacity of our structure. Also, it is conservative to assume that the beta is equal to 1, and beta is just the ratio of shear demand to shear capacity between level X and the level below it. Hence, beta is just equal to Vu divided by 5En, and assuming beta to be equal to 1 is a conservative choice, okay guys? And now we need to compute the stability coefficient, and we need to check if we need to include the P delta effects inside ETABS software. And of course, to do that, we will use the Excel sheet that we usually use. And we need now to obtain the gravity loads which donated by P in the stability coefficient formula. And I personally use all the dead loads plus 25% of the live load to check the P delta effects. However, most of the engineers use all the dead loads plus 50% of the live load. And this is due to the reason which I have shown you before in tutorial number 15. I have shown here at the end of this video the service load combo that should be used to check the drift limits due to the wind loads. And we can use the same load combo to check the P delta effect. Okay guys? Then now we need to go to ETABS and to obtain the gravity loss. And of course we need to define previously a load combo for all the dead loss plus 25% of the live load. Then this is the load combo that we need to use for now. And we need to obtain the story forces. And we need to export this table to the Excel. And of course we need to copy the gravity loss located at the top location of each story. Then I will use here the top location. And we need to copy those values to the Excel sheet. And before that, let me delete those cells that requires an input from us to make things more clear. And we need to copy the gravity loss to those cells here. And now we need to obtain the shear forces due to the equivalent lateral force procedure in X and in Y directions. Then let's go to ETABS again. And from the same option, which is the story forces, we need now to use the ELF applied in the X and in the Y direction. And let's clear here those load combo and load patterns. And let's export this table again to the Excel. And as shown here, we have the same shear force in story number 8, even if we choose different steps. Then it doesn't matter if we choose step number 1 or 2 in this case, okay? And of course, we need to use first the ELF applied in the X direction and the top location here. Then we need to copy those shear forces to those cells here. And now we need to just do the same for the Y direction. We need to choose the ELF in the Y direction. And we need to copy those results again to here and then from here to here. Lastly, we need now to obtain the displacements in X and in Y direction for those two locations due to the ELF in X and in Y directions. Then we need to go to ETABS, and I will set the plan view to story number 8, and I will choose here the all stories option. And I will select this joint at the middle, which is the center of mass location. And now we need to obtain the joint displacements, and we need to export again the results to the Excel. And as shown here, the displacements are not the same. Hence, we need to use the step number which leads to the highest displacement. Then let's filter first the results. And for the ELF in the X direction. And by checking it, we can see that the step number 2 will lead to the highest value of displacements. Then I will choose step number 2. And we need to copy those results to our Excel sheet. Let me copy them to here, and note that the displacement units is converted to millimeter. Then that's why I multiply by 1000. And we need just to copy the other displacements in the Y direction. And again from here to here. And now we still have the flexible zone location, which is this joint at the corner here. And from the display show tables, we need to obtain the joint displacements. And again, we need to filter the results and to check which case will provide the highest value. Then let me choose first the ELF in X direction. And by checking the first 3 rows here, we can find that the middle row have the highest value, which is the step number 2. Okay, guys? Then let's choose step number 2. And I need those displacements in the X direction. And now for the ELF in the Y direction. We need to use step number 2 as it provides the highest value. Add to here. Then as shown here, guys, the stability coefficient doesn't exceed the 10%. Hence we can neglect the P delta fx as mentioned by the code. And in our case, the stability coefficient is just around 1%, which means if we include the P delta effect now inside ETABS, we would have an incremental increase in the internal forces by just 1%. However, it is permitted by the code to neglect the P delta effects when it is less than the 10%. Okay, guys? Also, it is wrong to compute or to check the P delta effect using the response spectrum analysis load cases, as this is the peak response and the drifts obtained here in this situation or in this case are not occurring simultaneously due to the applied loads, and that's why it is wrong to compute or to check the stability coefficient using the response spectrum analysis method. And it is clearly mentioned in the code that we need to use the static forces to check the P delta effects, and we don't need to use the RSA method. Okay, guys? Hence, this is actually all the things that we need to talk about. And lastly, if we need to include the P delta effects, we need just to go to this option here, and we need to choose the iterative based on loads, and we need to add the load patterns that we need, for example, the super dead here, and we need also the live load, and I usually use the 25% as I have mentioned for you. And that's actually all what we need to do inside ETABS. And if I run the analysis now, the P delta effect will be included, but I will not include it. And this is the end of this tutorial. I hope you find it useful, and please stay tuned for my next video.